This call is now being recorded.
So hi everyone, we're glad to have Ronak today with us. So Ronak, let me introduce Ronak quickly. He did his PhD from TIFI Mumbai and his first postdoc from Stanford, and now he's doing his second postdoc from Cambridge. So he will talk to us about a bridge to the island, steps on the way from EPR to ER. So Ronak.
Hi, thanks, Dharmalya. Thanks for the invitation to speak. I just turned off my video because the audio, like the stream, got stuck. So, anyway, uh, yeah. So I'm going to speak about this paper I wrote with Luis and Onkar, and I have kept this talk at a relatively like a large. I given it a large introduction so that as many of you can follow as possible. So if you're not following, please interrupt me and tell me I'm doing this wrong. Yeah, just like whatever you don't understand, just interrupt me. Okay, cool. So let me give you a basic introduction. So suppose you have a black hole and you throw something into it. Okay. Uh, and then you suppose it's a ball and suppose it's a red ball. How do you figure out later after throwing the ball inside that you throw in a red ball and not a blue ball, right? uh, the answer is that the black hole slowly radiates. It slowly throws out Hawking radiation. Okay. And for a long time people were like, oh, Hawking radiation is thermal. By thermal we mean that it follows the relationship between frequency and amplitude is like fixed, so there is no information in it, right? But then people, sorry, yeah, but it's not quite. If this was the case, if it was thermal, then there would be no information in it, so you would not be able to say that the ball was red or the ball was blue, right? Because the color information is information. And so people eventually said, actually, it's not quite thermal. There are these really small corrections. Okay, these corrections are not. These corrections are exponentially small. They are exponentially small in the black hole entropy. And black hole entropy is these are really tiny corrections. So right. So and people were like, okay, maybe all this information comes out in these tiny corrections over a long time, right? Uh, so this statement that because Hawking radiation is thermal, information can't come out, was Hawking's information paradox. And in some sense, this idea about corrections was the resolution to Hawking's paradox. Okay, but then things got complicated because Samir Mathur and later this paper by I should have written the names. Almeri, Marolf, Polchinski, Sully. These folks, uh, and yeah, these folks this, these folks in Samir Mathur in 2009, these folks in 2013 or 12, notice that there is a problem if you assume that a lot of information comes out in exponentially small corrections. Okay, so let me tell you the problem. So uh, here we have an ADS black hole. Okay, uh, so what does this picture mean? So at the, no, this is the wrong pen for this. Yeah, at this end, you have, so this picture is a Cauchy slice of the black hole. Okay, it's a particular spatial slice, and at the top end you have the boundary of ADS. The boundary of ADS has infinite volume, so it looks like a that the top kind of looks like a off to infinity. Okay, here you have the horizon. The horizon is like a construction in the spatial slice. It's the place where the spatial slice becomes very small, and then the interior again it can become big. So it looks like this bag. Okay. So this is going to be my cartoon for a black hole throughout this talk. And basically, one way to talk about what Mathur and AMPS found was that suppose that over time the black hole radiates uh, stuff out, throws out Hawking radiation. Okay, and you collect all that radiation and you put it into a bath. Okay, put it into a bath here. Right. So over time, what happens is that the radiation is oh god, I'm sorry. The radiation is entangled with stuff that's inside the black hole. So when you throw the radiation into the bath, you get entanglement between the inside of the black hole and the bath. Okay, and this is my cartoon for entanglement. Little lines going across between two systems means that those two systems are entangled. Okay, so you have the setup. Now the CFT is in a thermal state. Okay, so it has a certain number of states, which I'll call dBH, which is this exponential of the black hole entropy. Okay, and basically because the CFT is in the thermal state, bounded by the black hole entropy. Okay, you can't put too many states into the CFT. If you try to put more states, you will increase the energy, but we are not changing the energy here. Now there's a paradox. As I mentioned, stuff right outside the black hole and stuff right inside the black hole have to be entangled. This entanglement is required just by the fact that the horizon is a smooth surface. And basically, it's just a property of quantum field theory that if you take 2 points which are very close to each other, the degrees of freedom at those 2 points are very highly entangled. This is how you get a smooth space-time, right? Smoothness is when nearby points are very deep, very highly correlated. But over time, you can get to a point where the entanglement in these lines is bigger than SBH. You just keep throwing radiation into the bath. Okay, you keep throwing it till the entanglement becomes bigger than the black hole entropy. Okay, so now you have this. So clearly, right. The CFT, of course, cannot have more entanglement than the black hole entropy. So that's basically a violation of monogamy of entanglement, because whatever's inside has to be entangled with the bath, right? Because there's just not enough states in the there's not enough states in the CFT to be entangled with the bath. Whatever's inside has to be entangled with whatever's outside. Okay, so you have that whatever's inside has to be entangled with whatever's outside and the bath. So this is a violation of the monogamy of entanglement, which says that a degree of freedom can only be maximally entangled with 1 degree of freedom, not 2. Right? Right. And basically all we assumed here was that the information comes out, which that assumption was in the statement that this stuff and this stuff is highly entangled. That whatever information is there in the interior, you can get it out from the exterior because it's entangled. Yeah. So this is the AMPS paradox. And recently, in 2019, people resolved this paradox using what is called the complementarity hypothesis. Okay. Black hole complementarity, which just says that what's happening here is that the interior is not a separate subsystem of the radiation. The interior is a part of the radiation. Okay, like this symbol in the middle is literally the set theoretic inclusion symbol, right? So how did they prove it? That will take me a few minutes to explain. So in ADS-CFT, whenever you want to calculate the entanglement of some boundary system, in this case is the bath, or what I'm calling radiation. Okay, what you have to do is that you have to take the minimal the minimal extremal surface X, okay, and basically the entropy is the area plus the bulk entropy of that minimal extremal surface, right? So the statement is that when basically the entanglement is at early times in this process where you're throwing radiation into the bath, at early time there are few lines, only 2 or 3 lines, right? And at late times there's like many 4 or 5 lines, right? It's just the empty surface which has zero area, and the bulk entropy is the number of lines over here, right? And so this is when the number of lines is small, the bulk entropy is small, and this is obviously the minimal amount of entropy you can have between the bath and everything else. But as you increase the number of lines to a large number, okay, you find that the number of lines becomes greater than the black hole entropy. It becomes really big. And then you find that there's a different extremal surface you can find, which is here. It is the black hole horizon. When you take the black hole horizon, the area is of course the area of the black hole horizon. And as all of you know, black hole entropy is proportional to the area of the horizon. The bulk entropy is just some order 1 number. It's not too important. So when the number of lines becomes very big, the black hole horizon becomes a smaller extremal surface. So the minimization condition picks out the black hole horizon. Okay, so you have this change in the when you calculate the entanglement entropy of the radiation, something changes. In the early stages, the entanglement entropy of radiation was given by the number of lines. In the late stages, it's given by the area of a horizon. Okay, good. Right. So this statement that the entanglement changes in form is called the page curve. And you can draw it like this. If this is time, this is entropy. As you keep throwing stuff into the bath, first, and then there's a transition in the minimal extremal surface, and you continue throwing stuff into the bath. So the black hole is getting smaller and smaller throughout this process. So after the transition, because the black hole is getting smaller, and the minimal surface is the black hole horizon, the area is getting smaller, and therefore the entropy starts getting smaller. So it starts going down. Okay, so this is called the page curve, and this was one of the right. So now you can ask, this is a cool statement, but what does it have to do with the AMPS or Mathur paradox? Okay. The point is that where it connects is what's called the entanglement wedge reconstruction hypothesis, which says that everything inside the surface X is part of the radiation. So, in particular, at late times, everything here becomes part of the radiation. Okay, any operator, the precise statement is that any operator here okay, can be reconstructed by an operator in the radiation. So basically all the effective field theory degrees of freedom inside the black hole are actually in the bath. They're not in the CFT. Okay. So this means that the interior is part of a radiation. So the fact that interior is highly entangled with the exterior is not a problem, because well, the interior is highly entangled with the radiation because the radiation is highly, sorry, the interior is highly entangled with the exterior because the radiation is highly entangled with the exterior, and the interior is just part of the radiation. Okay, good. Is everyone with me till now?
Yeah, go on.
Okay, cool. So now let me give you a very simple example of entanglement by reconstruction. Okay, Maldacen and Susskind actually, though I say that this was proven in 2019, this was kind of written in this, written down in this very fun paper by Maldacen and Susskind in 2013. It's a very Susskind paper in that it just comes out of nowhere. There's no proof, but it turns out to be right. Okay. So what they did was they drew an analogy with a very simple situation. So just consider ADS3 CFT2. Okay. ADS3 CFT2. Just the most basic, one of the most basic examples of ADS CFT. Take a boundary region A, which is the union of A1 and A2. Okay, just two boundary region, which is the union of two intervals, so that the total length of A is bigger than half of the length of the boundary circle. And take the CFT to be in the vacuum state. So it is dual to global ADS. Okay, good. Now, when you do that, the HRT surface is the blue thing here. Okay. Yeah, the minimal surface goes between A1 and A2. Okay. Now there's something very nice. So A1, remember A1. Okay. This is A1. An interval in a QFT, in a relativistic QFT, okay, is actually, you should think of it as a causal diamond. Okay. You just take the interval, shoot light rays up like that, shoot light rays down, and anything in this little diamond region is actually in the interval. And I've drawn Y here. If you take an operator up, any operator in the diamond, you can Heisenberg evolve it into the interval. Whereas if you take an operator here, oh wow, sorry, yeah. Whereas if you take an operator here, you Heisenberg evolve it. A lot of it is outside the interval. But if you take an operator in the diamond and you Heisenberg evolve it down, it stays in the interval. So basically the A1, you shouldn't think of it as an interval, but you should think of it as a causal diamond. This is just a basic statement about how you should think of subregions in relativistic QFTs. Okay. And now, this causal diamond, you can think of it as part of the, so this is in the CFT. Now, you think about it in the bulk. This causal diamond is here. Which is on the boundary of the ADS space. And then again, you can draw light rays, which are drawn in green. And you get a bulk causal diamond associated to the boundary causal diamond. And this bulk causal diamond is called the causal wedge. I am running out of space. I apologize for this. Yeah. And I have drawn the causal wedge again in this diagram up here. Okay. And you see that the much bigger than the causal wedges of A1 and A2. Right? There's all of this stuff in the middle. Right? And so entanglement reconstruction says that an operator phi is actually some operator in A1, A2. Okay. And in some sense, this is very much the same mystery as above. So the same surprising thing as above, where phi was the reason it's surprising that this phi here is a part of the radiation is that the interior of the black hole is not causally connected to the radiation. Again, here you have the fact that this phi is in a region that's not causally connected to A1 union A2. But it is still a part of A1 union A2. Okay. The only difference is this seems less surprising a priori because there is a smooth geometric connection between the phi and A1 union A2, whereas here there is no geometric connection. Right? There is just these lines, and these lines are just entanglement. It's not geometry. What Maldacena and Susskind said is, look, these are very similar situations, okay? It's just that we have aesthetical preference for geometry. So why don't we just say that the lines are geometry? This is known as the ER equals EPR hypothesis. It says that if you have a bunch of, so for the simplest case, consider two black holes. So the radiation system is another black hole. So you've been throwing radiation into the black hole here. So now the interiors of the two black holes are entangled. It belongs to the radiation, the right black hole, which is also the radiation system. Okay, this is why I called it radiation and not a bath, because right and radiation both come from R. And Maldacena and Susskind said, why don't we just hypothesize that when this happens, actually you get a wormhole between the two black holes. Okay, they just said this. They didn't really have much reason to say it. They just, yeah, but they just randomly said it. So this is called ER equals EPR because the lines are entanglement. So they're like Einstein-Podolsky-Rosen lines. And these entanglement lines become a wormhole, which is an Einstein-Rosen bridge. Okay. Good. Now you can ask, okay, can we prove this? We've proven the simple statement, which is that the interior is part of the radiation. Can we prove that entanglement becomes geometry? Which can we prove ER equals EPR? Okay, so this is the question that I wanted to do, that we wanted to deal with in this paper. So again, I will stop for questions, and also I'll have some water. So. All right. So the first statement is, so the first issue we ran into when we thought about how to prove this is that the question is completely meaningless. Okay. So there is the usual statement that a thermophile double, okay, in the boundary is just some a superposition of. But a thermophile double is dual to connected geometry. It's dual to an ER bridge. But the left hand side of the equation is just some superposition of disconnected geometries. These E microstates are just some geometry without a wormhole, and they become a geometry with a wormhole. Okay, nothing interesting happened here. All that happened was that you took a superposition of many geometries without a wormhole, and they become a geometry with a wormhole. Okay. What this means is that the question of is there a wormhole cannot be probed by a linear operator. Because if you could probe it by a linear operator, suppose there was some operator that gives 0 when there is no wormhole and 1 when there is. On the left hand side, very clearly you would get 0 because it's just a superposition of a disconnected geometries, and and your operator annihilates every element of the superposition, so it annihilates the entire superposition. But on the right hand side, we want it to be 1. Okay, this was argued, shown in a nice paper by Burrows and Wall in 2013. Well, not shown, well, pointed out. It's a kind of obvious statement in hindsight. But and there is also this very beautiful paper by Jeffress in 2017, which gives a bulk interpretation of the statement, and it's very much a Jeffress is very much worth reading paper. Okay, so what we did was we said, okay, if it's a meaningless statement, it's a meaningless statement. Let us just calculate some correlation functions in the boundary theory and see which bulk geometry dominates the calculation. All right. So if we did 2 models. The first model is what's called the double PSSY model. PSSY stands for Pennington, Schenker, Stanford, and Yang. They have a paper in 1912.xxxx. So basically this is December of 2019. So what they said was, look, okay, you have some black hole, right? And the black hole has interior degrees of freedom. The problem with interior degrees of freedom is that they're spread all over the interior, okay? There's one guy here, and there's one guy here, and there's one guy here, and there's one guy here. So it's a pain to keep track of where each little point is. Okay. So let's make a toy model where we put all of the interior degrees of freedom in one place. Okay. So what they do is that they lop off the interior, put a brane, put what's called an end of the world brane, okay, and say that all the interior degrees of freedom are concentrated on the end of the world brane. And then the entangle. So this was, when you do it with one black hole, it's what's called the PSSY model. We did it with 2 black holes and entangled the branes inside 2 black holes. So we call it a doubled PSSY model. Okay. So the lines between the the black lines that go between the red things is the fact that the 2 end of the world branes are entangled. So to make this a little more precise, we go to a specific model of gravity, and that's basically a 2-dimensional gravity called Jackiw-Teitelboim gravity. Okay. So Jackiw-Teitelboim gravity, the Euclidean action, the part we care about, just looks like minus S naught times the Euler characteristic of your bulk manifold. Okay. This is going to be the only part we care about. So whatever calculation I'm going to show you in the next within this model is going to just be a matter of counting Euler characters, which, if you don't remember, is 2 minus twice the genus minus the number of boundaries. All right. Good. So now let me. So So what we will do is we will define a state in the 1D theory. Oh wait, good, it's back there. So we define a state in the 1D theory. So this picture up here is a 1D picture. What is so the statement is so good. The state we define is we take a particular pure state mu comma I in the 1D theory and do Euclidean evolution with the Hamiltonian with a like do Euclidean evolution of Euclidean time L with the Hamiltonian. Okay. And oh god, I've been using the wrong color. I'm sorry. Yeah. Which we draw this as the left hand side. We take we okay, which I have put a p of mu I there for reasons I won't get into. And then we draw the Euclidean evolution as a black line of length L. All right. And the bulk picture is going to be that one way of thinking of the left hand side is that you took a thermophile double, okay, which is a two-sided geometry, which has a thermophile double won't have the red dot, okay, and did a projection on one side. This is a projection. So now you no longer have an entangled copy of two systems, but you just have a state in one system. And the bulk picture for this projection is that it's going to be a source for an end of the world brane. And end of the world brane is exactly what it sounds like. The world ends there. There's nothing beyond it. Okay. Good. So the state we take, which I call psi, is you just take two copies of this guy. Okay. And then you just sum over the and the guy here has an index I. Mu is going to be a parameter which I will tell you about soon, which is not too important for us, but I is going to be the index, and which is going to sum over very many values of the value of the index I. Okay. And the fact that it's a joint sum, I will denote by this dotted line. All right. Good. Oh, sorry, there's a wrong statement on the right. I don't know why I wrote that. So what we will do now is we will calculate the norm of the state. Remember, everything we are doing right now is in some 1D theory. It's just these pictures are path integrals. Okay. So when you take the norm of the state, you take so this path integral creates a k. This path integral creates a ket. You take a bra and then you paste it onto the ket. So you get ket bra inner product. Okay. Now this is just this again is a 1D path integral. In principle, there's two sums over I. There's one in the ket and one in the bra, which I've drawn as I and j. Okay. Good. Now, the ADS CFT dictionary tells you that you should think of the 1D path integral as a boundary condition for a boundary condition for your gravitational path integral. Okay. So you're going to sum over all geometries whose boundary looks like this picture here. Does that rule make sense to people?
Yes.
Okay, cool. So I mentioned that these little red dots are sources for end of the world branes. Okay, uh, so the entire story is going to be that the end of the world branes can either go, can either go like, okay. Why is this happening? One second. Oh, sorry, I had the wrong one. Okay, yeah. Okay. This obviously like both of these satisfy the same boundary conditions, but they're topologically different ones. Okay. And now look, we can evaluate these two path integrals very nicely. The one on the left is is topologically the bulk is a disk, right? The bulk is this region, and it's topologically a disk, so it has Euler characteristic 1. So you get e to the s naught. And then there are two sums over. Oh, sorry. Yeah. There is one sum over the index here and the completely different independent sum over the index here. Okay. And both indices go from 1 to k. So there's a k squared. There's a second contribution where the end of the world branes join up like the other way. And then there's just one sum over the index because the end of the world brane carries the index from here to here. So it has to be the same. So you get only one factor of k, but it's topologically two disks, so you get k e to the 2s naught, right? And this is really the main calculation of this talk. When k is much bigger than e to the s naught, the left diagram dominates. When k is much less than e to the s naught, the right diagram dominates. Okay. Right. So now, what does this have to do with bulk duals or anything? Okay. First of all, as being the number of lines is log k. Remember, our original motivation was to entangle two black holes. Okay, to see whether ER equals EPR held. So we created a toy model with end of the world branes and we entangled the end of the world branes. And the number of lines, the amount of entanglement is log k in this model. Okay, good. And so to understand the bulk dual, what we have to do is, is that you take these geometries. Oh, sorry, yeah, that's exactly what I wanted to write. You consider the moment of time reflection symmetry. Okay. And from the moment of time reflection symmetry, you can evolve in real time. Remember that these are Euclidean geometries. Because we've been doing Euclidean path integrals all of this time. But you can take a Euclidean geometry, look at the time reflection symmetric place, and evolve in real time using that time reflection symmetric slice as initial data. When you do that, you get the left diagram becomes the eternal black hole, and the right diagram becomes two black holes with end of the world branes behind the horizons. And there's nothing, as I've noted, there is nothing behind the horizon. That's right. There is nothing between the two end of the world branes. The space time really ends on the end of the world branes, and there is the space time is disconnected on the right. Okay. Number of lines was very big. Okay. S naught is basically a toy model for the black hole entropy. Sorry. sorry. S0 is the time model for the black hole entropy. And when log k, which again was the number of lines, is much bigger than S0, the left diagram dominates. And when the number of lines log k is much less than S0, the right diagram dominates. So what we are saying is that if we take two black holes and entangle them a little bit, they just look like two entangled black holes. But if we entangle them so much that the entanglement becomes much bigger than the black hole entropy, they become a two-sided black hole. They develop a wormhole. So this is a case where you go from EPR to ER in a particular toy model. EPR again remembers Einstein-Podolsky-Rosen, and EN is Einstein-Rosen. You go from entanglement to geometry. Okay. Yeah. So this is this is the main result from the first model. So I will stop here for questions. Is everything clear so far? Does anyone want me to go over any of the parts of what I said again, and so on?
No.
Yes, Rinkesh, we can hear you. Go ahead.
Yeah. Can you scroll a bit up? So the bulk here is 1 plus 1D. That's the thing you have the plus blue line, and the CFT is 0 plus 1D, like the SYK model living in the black lines there, right?
Yeah, exactly.
And the lines basically represent the Euclidean time evolution. As in different points on the line is different Euclidean times, right?
Yeah.
Okay. And can you scroll down a bit now? In this diagram, where in the right diagram, you have this end of the world branes as the vertical red lines. What is that horizontal I dot dot dot? As in, you said that's the index that is in some way, but you have drawn it between the end of the world lines as if it means.
Yeah. So right. So I perhaps wasn't clear enough about this. I am using these dotted lines as just a statement to say that the indices are the same across these two endpoints. Okay. Right. So this guy here. Oh, sorry about that. Yeah. This guy here is just sum over mu I. Okay. So which I have drawn as this dotted line here. Okay. And similarly, these dotted lines are that. And I just wanted to show that there's, again, you have a similar entangled sum over here. So I've drawn it as a dotted line. But yeah, it is not a part of the geometry. It's just a visual representation of something.
So basically, when you calculate with different indices of I, you kind of enforce that if you have a certain index I on the left side, you have the same not I dash on the right side.
Exactly. Let me write it in a more clear manner. This is just sum over I equals 1 to k of this guy. It's literally a superposition over different. Yeah, that's exactly what you said is right.
Isn't this picture kind of they have a single end of the world brane, and from which as in the two vertical red lines are basically one, and there is a you can construct the bulk towards the left as the left half and towards the right as the right half.
I would not say they are one, because basically, if what you're suggesting is that it kind of looks like this. Okay, but if it did do that, then basically you would be able to throw stuff across. Okay, and you really can't in this model. Like you can show that nothing goes across it, which is why it's more useful to think of it as two separate spacetimes. If they were part of the same spacetime, we could always do something and make it cross.
So if we use this to prevent throwing stuff across, we can use the hard boundary kind of, as in the Dirichlet
Yeah.
boundary condition.
Yeah, it is a property of the boundary condition that you cannot throw stuff across two different guys even if they have the same index.
Yeah. Okay. Thank you.
Yeah. Yeah, no, no, those are good questions. Thank you. I should have been clearer about some of those points. Hmm. Cool. Any more questions? By the way, if I say nothing else in the talk, it's fine. It's actually fine. This is a good endpoint for a talk. There's a second model which I can go into, but if people want to ask more questions about what I've already said and understand it better, that is also very good.
So Ronak, is it like not that psi is dual to some geometry, but that different geometries contribute to the psi inner product? That's what we're saying here.
There is no bulk dual is not some deep statement about a state. It's just some statement about what geometry dominates some path integral.
Right.
Yeah, and in general, you can like look at correlation functions. So, instead of we took a particular, you could have taken any correlation functions and look at bulk duals. The norm is a special correlation function of the operator 1. Yeah. Yeah, but yes, it's very important. These papers of Marolf, Wall, and Jafferis, one of the important points they make is that bulk dual is very, very much an effective theory concept. It's a statement about something dominating a path integral. It's not a statement about a property of a state.
Right.
Yeah. No, that is the central philosophical point here. I thank you for.
I think there are no questions, so you can proceed.
Okay. So now I'll give a second model, which is dynamical. It might, this one is more, might be harder to follow for people who are not very familiar with the field. So don't worry if you get lost. Okay. And the basic point is that the previous model, the problem is that we entangled two black holes by fiat. We just came and said, hey, let's make up some degrees of freedom and entangle them. But it would be nicer if you took two disconnected black holes and entangle them in real time. So I have shown one way to doing that here. We take the same sort of black hole we did earlier, two black holes, which are these two path integrals. Okay, with the different end of the world indices anymore. So at the Euclidean evolution does not entangle them. They're disentangled here. Okay, and what you do is then you couple the two systems, okay, which I've drawn as a thick line, and you evolve in time, in real time. When you do that, over time they get entangled. You take two things, you couple them, they become more entangled. The basic fact of life. Okay. So the first thing to notice about the state is that they're being entangled by a unitary operator. So the norm at time t is equal to the norm at time 0 because time evolution is unitary. So the norm of the state will be exactly the same as the norm of the unevolved state. So looking at the norm won't help us anymore. We won't see any interesting stuff there. Okay. So what we do is we look at some correlation function. Okay, of some operator O. So okay. By the way, sorry. One thing I wanted to say is that the GT gravity is coupled to a 2D CFT in the bulk. We still have a 1D CFT on the boundary. There's a 2D CFT in the bulk. Okay, and O is an operator in the 2D CFT. Okay, and the value of this correlation function is you sum over all of the saddles that you can possibly write down. Okay, each saddle will have a different CFT state because it's a different geometry. So you calculate the expectation value of the operator in the particular saddle. With e to the minus I, the gravitational action. Okay, this is a funny statement about CFTs coupled to gravity. In a CFT itself, you would just sum over all CFT saddles. Okay, but when you couple it to gravity, you calculate the correlation function in all geometries satisfying the boundary conditions and weight it with a gravitational weighting factor. And gravitational weighting factors, remember, are very big. Like all gravitational actions go as 1 by G Newton. G Newton is a tiny number. It's like the smallest coupling constant we have in nature. Okay, so 1 over G Newton is a huge number, and e to the 1 over G Newton is a especially big number. Okay, one small comment for experts is that instead of O, you could have even taken O1, O2. The only important thing is that O1, O2 should not have identity in the OPE. Okay, I won't go further into that point. So let me tell you. So now the point is that in this state, the set of saddles is the same as the set of saddles in the that we looked at in the first model. There's a disconnected saddle and a connected saddle. The only thing is that now you couple them and couple the boundaries and evolve them. So disconnect. So whenever you couple the boundaries, you throw in some shocks. Okay. Over from coupling boundaries. Right. Sorry, I should look at the left diagram first. So this is the disconnected saddle. You throw in some shocks when you couple the boundary. Okay. So that just changes something irrelevant. It won't matter too much. Okay. So again, but you still get two black holes with the end of the world branes, but you get stuff going. If you have some information here, it goes right across. But if you have information here, it bounces off. Okay. I apologize for this picture. We made this picture for our paper, and that's why it's here. But it's actually a really terrible picture, which does not convey enough information. Okay. The other case is to basically ignore all the green lines. It's just random details which we should not have included in this picture. The other case is that you took a connected geometry, so you have a what? Oh, yeah. You basically have a connected geometry here. Here it's a disconnected geometry. And again, you throw in some shocks. Okay. When you couple it, and then now that has the property that anything that goes right here comes out of this side, but anything that goes here comes out like this. Okay. Good. And the most important thing is that the temperatures of these two black holes are of these two geometries are different. In the left geometry, you basically have two copies of time evolution, Euclidean time evolution of length L. Okay, and the way thermophile doubles work is that this implies that you have two black holes whose temperature is 1 by 2L. On the right geometry, you have one big Euclidean time evolution of length 2L. There's also an extra length associated to the end of the world branes, but you can send that to 0, which is what we'll do. So it's effectively length 2L. And that implies that the temperature is a factor of 2 colder than the disconnected geometry. Okay. But the disconnected geometry has the topology of 2 disks in the Euclidean section, and this is still 1 disk. So disconnected geometry is enhanced by the topology, but is colder, but is hotter. Okay. And now here's a basic point. It is just a basic property of black holes that 1-point functions in a black hole background decay like e to the minus 2 pi temperature times time times the dimension of the operator. Okay, this is just this is called a quasi-normal mode calculation, but it's just kind of a known thing. Which in this case, I'm going to set delta equals 1. Temperature is 1 over 2L, so it becomes e to the minus pi t over L. The same calculation on the right hand side looks like e to the minus pi t over 2L, because the right hand side was colder. The connected geometry was colder. So even though the disconnected geometry starts off with a large contribution of e to the 2s naught, it's decaying a factor of 2 faster. It's decaying faster than the disconnected geometry. It's at delta equals 1. Okay. So when the time becomes very large, the connected geometry dominates over the disconnected geometry. When time is small, the disconnected geometry dominates. Okay. But here's the thing. Way to think about time is there is also an amount of entanglement. When you couple two things and evolve them, they get entangled more and more in a linear fashion. Okay. So the entanglement increases linearly. So what this is saying is that for this correlation function, when the entanglement becomes big enough, the connected geometry dominates. So this is also kind of the same thing where we increased the entanglement and found a connected geometry. But it's very much a kind of that because we had to look at this very specific correlation function, and it's not clear what that means. So this is the second result. This is the result of the second model. And between this and the result of the first model, these are the main points I wanted to make, that there is this weird relationship between the way the black hole complementarity and ER equals EPR, and you can actually make that explicit in some ways. And so yeah, that's really all I wanted to say. Thank you.
Okay. Thanks, Ronak, for that very excellent talk. So let us all thank Ronak for the talk. And now we will open the floor for questions.
Hello again. So can you scroll up a bit again?
Sorry, can you speak louder?
Can you scroll up a bit? Hello.
Oh, hi.
Oh, can you scroll up a bit? Yeah, there. So in the left diagram, it seems like in very early time the geometry was connected and somehow it got disconnected by that oval shaped thing, and then it get connected again. So can you explain?
I'm very sorry. This is a terrible picture. Okay. So actually, we should ignore this part, and you should ignore this part. Okay.
Oh, so the geometry starts from that point. Okay.
Yeah. I don't know why we drew this picture. It was like one of a very stupid decision in hindsight. Yeah. Like
So Isn't this picture kind of similar to the in the previous model what you showed, the two vertical lines? Here the edges of the oval being the two vertical lines, kind of the end of world branes from where if you throw something it gets reflected.
It's almost that, but I kind of inverted it. So these are still end of the world branes. Okay, and this is the ADS boundary. Okay, let me change the color of this so that it's more easily visible. Okay. Okay, so basically what I did was I took this picture and I flipped both of them to make the boundaries come close to each together, rather than the end of the world branes. Okay, so basically that's what this picture is. The reason we did that was because now the boundaries are coupled, so we wanted them to be together. But yeah, it's like the same picture except I did that. I don't know if you're looking at the screen, but yeah.
So it's like instead of having the same index now, that was the coupling on the previous model, and you're
Yeah.
kind of coupling with the boundary in this model.
Yeah, yeah,
Yeah.
yeah. Sorry about these pictures. It's not well thought out. Yeah.
One more thing I want to ask, in the very beginning, in the AMPS paradox,
Mm-hmm.
if you can scroll there, it would be a bit easier. Yeah, so this picture,
Mm-hmm.
the Mathur AMPS picture. So initially, you said, so the problem is you cannot have entanglement entropy more than the black hole entropy, since the black hole shrinks and you have a limit to the black hole entropy because of the Bekenstein's bound.
Yes.
So here, isn't this like when after you reach that bound, whenever the black hole emits new radiation, it's like the old radiation and some part of the old radiation gets entangled with the new radiation, and the remaining part of the old radiation is still coupled with the black hole radiation, and we
Uh,
kind of don't know which is which, so we have this
yeah.
problem of one of them. Can we think that like this?
Yeah, exactly. So old radiation is really what I'm calling R here, because all the old radiation has been put into the bath. And so the old radiation has to be completely entangled with the new radiation simply because there's not enough, the entire CFT is completely entangled with the radiation. So yeah, and the new radiation has to be completely entangled with the interior mode because it's a smooth horizon.
So we can say the entanglement radiation decreases after a particular time because the whole entanglement radiation started because we sliced the pure state into two different subspace, as in subregions, and now the entire the some part of region A comes to the complement part, so the entanglement decreases as a whole.
Yeah,
So
basically.
which is captured by the area of the horizon, and hence that term dominates.
That's right. Yes.
Okay, thank you.
Any other questions, comments from anyone? So Ronak, in the standard, you looked at this pictures where there were two black holes.
Mm-hmm.
So if someone were to look at like a black hole and a bath, I mean, did you look at something like that, like a black hole and a bath?
Sorry, what? The
Just
black
one.
hole and bath thing was calculated done by these papers, right? The Pennington and Almeri, blah blah.
Right.
Yeah.
And I was just wondering, like, yeah.
Yeah. So, but that case was already done, and you could ask whether like you can like. There are other cases where you can actually put some non-gravitational system, more of a non-gravitational system between the two black holes and so on. And that's a simple generalization of our calculations. actually, and so on. But yeah, I think just purely coupling a black hole to a bath is was done before us, and what we did new was make the bath in another black hole. Yeah.
Yeah, I mean, yeah, that was, yeah, that is correct. That was done. So
Hmm.
in that case, we wouldn't be getting a different geometrical contribution, right? It will be just be
Yeah,
change in.
so in that case, the geometrical contributions are not interesting for correlation functions. You have to look at entropies, in which case, and those are more interesting there. But yeah, like for correlation functions, you don't see anything interesting there. That's true.
Mhm. Yeah, I was just wondering if there are some other geometries there also, which
Yeah, not for correlation functions.
okay.
Only for multi-copy quantities.
Right. Okay. Okay, so if there are no other questions, let me thank Ronak again for the excellent talk.
Thank you all. Thanks for the questions. Yeah.
Before you end,